class. Okay, so the title is like that, and you probably don't understand it, most of the word. Don't worry about it. You won't understand most. So anyway, so to give you a glimpse about what I have been doing, my research interest is I had four categories. One is the stochastic and order approach, and incidence among the data, the joint work with record worker and Kubinsky as the first more material short. And the second part of my research is about the feedback-based decision-making in the world with Professor Levinson and Eugene of the National Taiwan University. And I also give doing some work on frequency of complex information function with the stock concept with after this global in the US. Today, my talk is mostly related to the impact of law of similarity on AI representation. This is a joint work with Jeff Iris and UC Irvine. I just came back from the US 2 weeks ago for my sabbatical in UC Irvine. I'm working with Jeff. So here we go. Online, I will introduce the Fact-Narrow and AI representation, so talking about the fact problem and the realization of AI representation. Then I will introduce what we call homogeneity laws, including the nearness to neighbors law, the Romani's power law, and also the focus of this talk is the power law of similarity. Then I will show you some current progress on the work on the impact of this similarity on the AI representation. Louder? So it starts from Beckner. Okay, everybody knows he is the founder of psychophysics. That U be a function representing the sensory scale. And Beckner, about 1850, he came out with what he called the big intuition, big achievement about the Cauchy model psychophysics. He has two assumptions in his model. The first one is that internally, you can explain it as in sensory scale inside your brain. He said that there are two stimuli. One is X, the other is S plus delta S. This delta S means the JNP, or you call it the Weber function. And internally, you will compare these two stimuli, and then you make the subtraction. And the resulting scale does not depend on the X. So if you look at the right-hand side, that everybody knows from the psychology course that the bottom line, the bottom part is the sensor, is the physical intensity, and the top line is about the sensation, magnitude. So that's the first assumption he made. And the second one is that he assumed that the Weber's law holds, namely the Weber function divided by x is a constant. Then he used what he called some calculus basically, and he derived what we everybody knows the logarithmic law of psychophysics. Do we have a pointer? Yes. Okay. So this is the law of psychophysics. And later work, people have shown that if you look at the JND, this part, the delta part, actually it depends on the criteria you use. If you use a cutoff like a 0.71 or 0.84, you will get a different delta. Like, so here we say very often a cutoff pi, because the pi between 0.5 and 1 is implicitly assumed for the estimation of JND. So including Duncan Lewis and the Enter in the 1960s, they say that we should take the probability cutoff into account and write delta indexed by pi of x. So these are early work of the Wagnerian part. And also Lewis and other people, they revised, formalized the Beckner's formulation. They said that Beckner's idea is actually about finding an algorithm for the construction of a real value strictly increasing function u, such that the probability that you just x is bigger than y is a function of f, and inside your frame you have probably one scale u of s minus u of y. So this is what we call the secondary representation, where f is strictly increasing and continuous. And the later work by Lewis and Edward, they showed that in fact, Fechner used the wrong mathematical tool when he derived his log law, because he used a calculate differential equation. Actually, we should use the functional equation, but not the calculus differential equation. Lewis and Edward showed that the scale u, if you use the functional equation technique, you can still derive that u is a log function. Okay, and but also it only holds for the spatial Weber function. And later on, Michael Levine, Felix Ruby's student, and Felmani, they studied the condition that must be satisfied by a more general Weber function in order for the solution of u. And David Krantz, 1971, he also a German psychologist, Fong Hsu, 1962. They show how to construct the scale. You use it, what we call the Fechner method of integrating J and D, given that the solution to U exists. So our work, the work I'm doing with GF is, we follow this line of using this kind of tools, process some calculus integration and the functional equation to work on what we call the A-band representation. So, okay, what is a A-band representation? If you follow Michael Levine's work, actually you can write the representation. There are two kinds of representation. One is that you have if you remember the Fechner representation, it looks like this, right? Inside f is a function, and inside you have one function, u of s minus u of y. So probability that you adjust s bigger than 1, the function of f, and inside the function. And right now we just extended. So here you have u of s times h of y plus g of y. And we call this the first kind. The second kind is that you have the multiplication part in the second part. And the Levine studied the condition for the existence of A-band representation. So let's pause here for a little bit. That I want to talk about the Weber's law. So Weber's law, everybody knows that you basically say that delta x divided by x is a constant. But in general, some data do not follow Weber's law. This is an example from Jensen and Reed in 1977. Their data look like this, and actually you can trace how beautiful he suggests that the delta s is a function of k times x to the power of alpha. Namely, if you write in terms of log, and both sides you divide by x, and when you take the alpha, you get this form. So this graph is the horizontal. The x-axis is log x, and the y-axis is high. So you can see that you can use the straight line to fit this model, those data, and the slope is just like this is alpha minus y. And later on, McGill and Goldberg, they actually coined this term as near-miss Weber's law. That's how the word came from. And in our notation, because we just say that we should take into account, put an index of the probability as an index when we talk about the Weber function. So in our notation, one kind of near-miss to Weber's law is like this, namely that delta index like pi of lambda x is a function of lambda x is equal to lambda to the power of alpha, alpha depending on pi, and times delta pi of x. But in this talk, I won't focus on this near-miss to Weber's law. Instead, I will talk about the other kind of near-miss to Weber's law. This is due to Fong Hsu. So the idea is that Felmani proposed that we should focus on what he called the sensitivity function. What is sensitivity? That's just the stimulus x plus delta of x. That's the plus equal sensitivity. So if you look at the graph here, you have a reference, and this is a GMD. So this guy is C of x. That's the sensitivity function. The y-axis is probability. So Galvani in 1985 and 1994, he talked about, he proposed a power function of C, the sensitivity function. So it's written very similar to the previous near-Weber just saw, but here we replace the delta with the sensitivity function. We call this the Galvani's power law.
Excuse me.
Yeah.
Is this a scale for subjective magnitude?
Yeah. And the Galvani also discussed what we call the balance condition, namely. For most experiments, if we balance, sometimes we present in a 2FGQ interval force choice test, we present the comparison scheme and the reference scheme, sometimes on the left-hand side, on the left side of the screen, sometimes on the right side of the screen. Then after you collect all the data, most people will probably just average the data. When you do this kind of practice, then automatically it's forced this equation will hold. That's what we call the balance condition. But in this talk, I will just focus on what we call the weakly balance condition. Namely, if you have two stimuli, they are of the same physical intensity, then the probability of judging that one is bigger than the other is 1/2. That's what we call weakly balance condition. Okay, so in our previous work that I did with Jeff Harrison and Cristobal in 2010, we consider this kind of affine representation, the one that you saw from Michael Levin, and we managed to show that a regular system with this affine representation can always be weakly balanced. And the second one is that we proved the uniqueness theorem of the affine representation. In particular, U is an interval scale and H is a ratio scale. And we also, in that paper, we showed that when this affine representation degenerates, well, there are several cases. We have shown that when we have the coexistence of the two kinds of affine representation, and also the balance condition will force this representation to degenerate to a Becknerian one. Why we say degenerate? Because the Becknerian representation is a special case of this affine representation. Okay. Then in that paper, we also talked about weakly balanced affine representation written in this way. So probability that x is bigger than y is a function of f, and inside you have us minus uy, but you also divide it by sigma y. So obviously, if sigma y equal to 1 or equal to constant, this is just a binary representation. Why we are interested in this kind of representation? Because for example, model based on search function case 3 looks like this. And if you assume that the standard deviation or the variance of x and the y are equal, then you can write the like this form, standard normal, and the form pretty much consistent with this weakly balanced affine representation. And in that table, we also show that the Galvani law forces this representation to be Becknerian. How many minutes left? 2? 4? Oh, no. So, I haven't started my... so, it's convenient to write f inverse pi equal to s. So, if pi is approaching 1, is approaching half, we have s approaching 0. So, this is the form that we have if you follow the work by Everson and the Krantz about the Beckner method in creating GMD. This kind of form is not very ugly if you're doing this here. Anyway, so we proved that we can recover the scale of a weakly balanced affine representation. The scale in that representation, U and sigma look like this, very ugly. Here you have U plus U of x 0 plus U, the first derivative of U, and you have the integral of something exponential of some integral, and then sigma also here when I use the omega and the f, these two terms. The f term is the first derivative of c, the sensitivity function with respect to s that you evaluated when s equal to 0, and the omega is for the second derivative. So anyway, so our focus is to see whether we can recover the functional form of u and sigma. But you know it's very ugly. But if you know the functional form of f and omega, then automatically you have some good idea about how u and sigma look like. So that's the focus. The current project I'm doing with Jen. So if we know the functional form of f and omega, then everything will be fine. So we also figure out in that theorem, in this theorem, there's some nice relationship between linking the F representation and the Fagnerian representation. Namely, if you write mu of S in terms of the first derivative of F and the minus the omega at ratio, and if this guy is a constant, or if equal to 0 or not equal to 0, doesn't matter, then it's a Fagnerian representation. Okay. So in other words, if sigma is a constant in the original weakly balanced F representation, then it's obviously it's Fagnerian. But the second case is that if sigma and the u, these two functions are linearly related, then also you can prove that the F representation is degenerate to Fagnerian representation. And Jeff Iverson proposed a law of similarity. Look very obvious here. So C lambda s equal to gamma times C x. But here we have some index eta. And this means gamma is a function of two variables, lambda and s. And this index eta is also a function of two variables. So Iverson solved this equation for see, there are total 12 family solutions. So as I said that we are trying to have a good idea about what the F representation, the U and the sigma in the F representation look like. But it turns out to be a very, very difficult work. So we are not that ambitious anymore. We just want to see under which condition the F representation can degenerate to the Fagnerian representation under the law of similarity. There are some nice property about the law of similarity. I don't have time to go through this. I just show that in end up we focus on special case. A more restricted case of the law of similarity here, instead of using gamma, we assume gamma. That function gamma is a power function lambda to the iota s. So there's also some nice property you can be proved. So far the main point is that if we assume that the weakly balanced atom representation and the power of similarity, then one of the following three hold. The first one, you can get a functional form of S. Okay. Remember we want the functional form of F and omega. But then the functional form of omega is very arbitrary, and unless you can confine yourself to work on when the Fn degenerates to Fagnerian. In that case, omega, in this case, is equal to ax. So we have a functional form of F and omega. This should be okay. And also you can prove it's a logarithm function. So one example is the Weber sum. It's a special case of this one. And the second case, we also get the functional form of F. In general, just assume it's 2, and it's a s times log x or something else. And the representation is Fagnerian if omega looks like this, very ugly. But in this case, you take the local form. But although it looks very ugly, in fact, one is called a special case of this one. And the third case is that f is a power function. And again, omega can take many different forms. But however, if this representation is also Fagnerian, then omega is also a power function with different compared with that. So in this case, can prove that the sigma is a constant and U is a power function. It is a magnetic. And the data from jet wear and the green can be recaptured by this form. This form is a special case in this case. So far, we have shown that basically when you put some constraint, just asking when the F1 rotation can be degenerate to Wagnerian, and you get 3 cases. But if you look at the Iverson's result, I told you that there are 12 family of solutions. 6 of them do not appear in the 3 cases. It's outside the 3 cases. So it must have something to do with the functional form of gamma. Because in the power law of similarity, we assume that gamma is a power function. So obviously, the 6th case that Iverson solved in 2006 is not included there. So why? This a further explanation suggests that the gamma, one of the 6 cases, I just showed it in the example, looks like this. Obviously, you can see this gamma is not a power function. Okay, we can also work on to solve the optimal form for beta. So, yeah, how many minutes? 0 minutes. It can work. So we're still trying to see, under the law of similarity, study the case in which the weighted balance F1 rotation is not determined into a narrow one, because that's the one that nobody has really studied. And the second future work is that you can also ask about the JNT-based law of similarity instead of the sensitivity function-based law of similarity, to work out whether its impact on the weighted balance F1 rotation. So that's it. Don't work with Jeff Iverson, and my work is supported by the National Ministry of Science and Technology. Thank you. Sorry.